concentration as well for solutions. We talked about molarity. And so we're going to kind of put that together, stoichiometry and molarity and concentration here. And we're going to talk really about what's sometimes referred to as solution stoichiometry, really titration type problems and what's going on with titrations. So let's talk a little bit about sort of what titrations are and some of the important parts of it. First off, when we do a titration, we oftentimes will do a titration to figure out certain things like perhaps the concentration of an unknown species. And we do that by using another solution that we definitely do know pretty much the concentration of. Usually when we do a titration, it involves a burette, which is what this little glass guy looks like here. That's a burette. And, we oftentimes will obviously have a flask, a beaker, or something like that. And really the titrations we're going to talk about mainly here are acid-base titrations. So a reaction between an acid and a base. And what we typically do is we add, say, from a burette, maybe we put some sodium hydroxide, some type of base up there. We have down there in a beaker an acid. And basically, we continue to add, for example, say something like sodium hydroxide to the beaker until really the reaction is done. And when the reaction is done in terms of sort of a acid-base titration, that's pretty much when we take an acid plus a base, we make a salt plus water. And when the reaction is done, that is what is sometimes referred to as the equivalence point of the titration. And the equivalence point of titration in a acid-base titration is the point in the titration where you pretty much have added the exact same amount of moles of acid and base. So that is when the moles of the acid in an acid-base titration equals exactly the moles of the base. And that's why it's sort of said to be done at that point. Now, when we do an actual titration, or when you physically do a titration, we oftentimes will stop at what is sometimes referred to as the end point. And the end point in a titration is pretty much like the name implies. It's the point in the titration where you go, I think I'm good, I'm going to stop. And if you do a good titration, usually your end point should be pretty much the same as your equivalence point. And that's usually the goal of sort of a titration when you do it, is to try to reach that equivalence point. So how do we know when we're doing a titration, should we stop? Should we keep going? Are we done? And that's really where an indicator is used for. So in an acid-base titration, or really any type of titration, we typically use an indicator. And the indicator basically is used to give you a visual reference of, hey, I think you should stop your titration, basically. So it was something that will change color. And ideally, you want to pick an indicator that will change color near the equivalence point. So something that will change color near that equivalence point. And again, that's sort of your visual indication that your titration is pretty much done. How indicators really work, and you'll learn more about this in 200B if you take 200B, but indicators basically work over a pH range. So over sort of a pH range, they will sort of change colors. So they have a specific color sort of in acidic solution. They have a specific color kind of in basic solution. And you're looking for one that basically will change color around, where your equivalence point would be. So a very popular one, and the one that they use here in the sort of this titration, is an indicator known as phenolphthalein. And phenolphthalein is an indicator that is colorless in acidic solution. It's actually colorless in neutral solution, but it turns a wonderful shade of pink there in basic solution. And that's because phenolphthalein, for example, works over a pH range of about 8.3 to like 10-ish or so. And when you look at the indicator around 8.3, it's kind of colorless in this part. And then as you sort of get above 8.3, heading towards that 10 color, it becomes more pink as you go this way. So it becomes more pink, super dark pink. I know that's red, but it's okay. We'll pretend it's pink. Super pink as you head down towards, this side. And this works really well for a lot of acid-base titrations and very common titrations that people oftentimes will use this indicator for. And you might have done it before in the past. Maybe if you did a titration of vinegar and sodium hydroxide. Vinegar is basically acetic acid, and acetic acid is a weak acid. And when you do a titration of a weak acid with a strong base, which is what sodium hydroxide is, when you reach the equivalence point, it's actually basic. And that's why this indicator works really well. Basic in terms of pH is above 7. So above 7 is basic in terms of the pH. And this works really well for this type of titration. And that's because if you actually calculate the equivalence point, it's somewhere in the neighborhood of like 8.6, maybe in that range, kind of 8 point something. And if you've ever done a titration or, done it before, and odds are you probably use this indicator, they usually yell at you that you want to kind of stop your titration when you see the very, very first sign of pink that basically stays. And the idea behind that is you need to go until you can kind of see the pink to indicate that it's basically changed color. But you want the lightest shade of pink, so light that you pretty much got to hold like a white piece of paper over it to kind of see the pink color. Because if you do that and you stop your titration at that point, you're probably in this area in terms of the pH. And that's really good because that's probably right around where your equivalence point actually is. Now, if you go really dark pink, like, I like to titrate over in this area over here, you probably have shot way past the equivalence point and you see this really, really dark color, and you might have actually passed the equivalence point and be pretty far away from it. The other thing that if you've ever done a titration before or have seen it before, there's usually a very common thing that people say when they do a titration, especially when they're using something like phenolphthalein as the indicator. They go like, hey, I was just, doing my titration. I added 1 drop. It went from like no color to like super dark pink. And the real reason that happens, and again, you'll learn more about this in 200B, is if we made like a titration sort of curve of what's happening, if this is the pH and this is like the volume of sodium hydroxide, what happens is as you're doing your titration, you get this titration curve that sort of looks like an S usually. And your equivalence point is, say, like right about there. And what we see is, and what usually happens as you approach the equivalence point in terms of the pH and in terms of volume is, it gets really, really vertical as you get near the equivalence point. And what that means is if you go kind of down here, you can add a very, very small volume in a titration, but it will change the pH a lot. So even though you maybe only added 1 drop, that 1 drop is enough to maybe change the pH from, a pH of 8 all the way up to maybe a pH of 9 or 10 or something like that. And that's why when you kind of do that with this sort of indicator, you will sometimes see yourself like, hey, my solution kind of looks like this, no color. And then all of a sudden it looks like way darker than this, like super dark, dark, dark pink. And it's because as you approach the equivalence point, basically it goes vertical, which means you don't have to add a lot of volume of base, for example, to change the pH by a lot. And even if you missed it by a drop or two, you could potentially see your indicator change pretty big in terms of its color, going from almost no color to super dark pink. And usually if that's the case and you're doing a pretty good titration where you're very careful and you're sort of adding drop by drop, you'll be okay, even if the sort of color went really dark pink. And that's because, again, you're vertical here, even though you might have missed it by a couple of drops. The overall volume for the equivalence point is going to be very, very close to the true value. Now, don't get me wrong, if you just open this burette up and let it flow in and you just decide after, a long time, shut it off, you may be way past your equivalence point, like way over here, and it's going to be the same dark color as it was over here. So, you know, if you're very kind of careful as you're adding, and you do sort of go drop by drop, especially as you get closer to the equivalence point. And you usually can tell you're getting closer, because what will happen is as you start the titration, you know, you'll drop it in, it'll turn pink, you'll mix it, it'll go away, you'll turn pink, it'll mix it, it'll go away. And as you approach the equivalence point, what typically will happen is that pink color will kind of stay longer and longer and longer, and you know you're getting very close to your equivalence point. And that is where you really want to kind of go slow until you reach the equivalence point. Any questions on sort of overview there of how titrations sort of work? So this is sort of physically what's happening when you do a titration. But what happens in terms of sort of calculation wise is it's really a stoichiometry problem. So it's a solution stoichiometry problem, and you kind of do these problems very much like all other sort of stoichiometry problems. The only difference is sort of how we get to moles. So because we're using volumes and we're using solutions, we really have molarity and volume a lot of times. So we oftentimes will use that the moles will equal the liters times the molarity. So in terms of normally how we sort of go grams to moles to calculate the mole, using the molar mass to calculate the moles in a stoichiometry problem, here we use really the molarity and the volume on the front end of the calculation. And a lot of times we'll use molarity on the back end of the calculation. So instead of finding out how many grams of something or anything like that, we oftentimes will figure out how much volume, what the molarity is. So the middle part of it is pretty much the same. You want to kind of do all your same 4 basic steps: balanced equation, convert to moles, mole to mole relationship. And like I said, sort of the difference is how we get the moles at the beginning and using molarity and volume at the end. So let's take a look at sort of a titration problem here together and sort of see how we should approach this. What volume of 1.42 molar sodium hydroxide is required to titrate 25 milliliters of 4.5 molar sulfuric acid? So again, this is a titration problem. It's really, again, a stoichiometry problem. So you want to kind of start with your same steps. So here we would want to start with a balanced equation. So we are reacting sulfuric acid with sodium hydroxide. And this is really a double displacement reaction. It's an acid-base reaction. So if you remember, as we just saw, when we react an acid and a base, we make basically salt and water. Water coming from the acid, so the H from the acid, the OH from the base gives us our water. And the salt part comes from the other two guys. So it's really the 2 positive ion switching partners. That's going to be sodium sulfate. And remember that we do want to make sure we get the proper formula down first. And that is the proper formula here for sodium sulfate, sulfate being -2, sodium being -1. And we want to make sure, again, we get that proper formula down there first. Now that we have it, right, we want to make sure that it is balanced. And it looks like we need to put a 2 here in front of our sodium hydroxide. And we might need a 2 over here in front of our water as well. So it really is just like a basic stoichiometry problem here. We're starting with our balanced equation. The next thing, just like a normal stoichiometry problem, is we want to convert to moles. So if we think about the information that's sort of given to us in this problem, what they gave us was we have the molarity here of sodium hydroxide. We also have the volume of sulfuric acid, and we have the molarity of sulfuric acid here. And we're looking for really the volume here of this guy. So in this type of problem, it's actually not necessarily a limiting reagent problem. And that's because we can only get moles from this piece of information here. So this is really the only piece of information we could get to moles. We can't get to moles here. We're actually looking for something here. So it's just a basic stoichiometry problem. The difference is how we're going to get to those moles is we're going to use this information here basically to get to moles. And we're going to do that by converting our milliliters into liters. So we can move the decimal point 3 places to the left, gives us liters. We're going to use the molarity of our H2SO4. And remember that number means that there are 4.5 moles per liter of H2SO4. So this is sort of the difference between sort of a grams to molar mass to moles and a solution problem. Here we use our volume and our molarity here, and we end up with something like 0.1125 moles of H2SO4. Any
Why is
questions?
this not an equilibrium reaction? Does sulfuric go? Does it go to? Does it fully separate?
Yeah, so sulfuric acid is a strong acid, and sodium hydroxide is a strong base.
Right.
So it won't really go to equilibrium in this case. Yeah. Now, if you had like HSO4 minus, you would have some equilibrium type problems. So for our purposes here, we don't go into too much in terms of equilibrium type titrations and stuff like that. So you could assume that all of these are sort of strong acid, strong base sort of combinations that go to completion. Other questions on that? Okay, so once we have moles of sulfuric acid, we are not interested in sulfuric acid, right? We are really interested in our sodium hydroxide. So the next part is really the mole to mole relationship, just like a normal stoichiometry problem. So what we're going to do here is from the equation, we could see that for every 1 mole of H2SO4, we get 2 moles of NaOH. So the next step would be to do that stoichiometry part. So write the right number there, 0.1125 moles of H2SO4. And that's going to give us 1 mole of H2SO4, which is the stoichiometry part, to 2 moles of sodium hydroxide. And that will get us 0.1125 times 2, 0.225 moles of sodium hydroxide. So now that we did step 3, we got moles of sodium hydroxide. The last step is to convert the moles to what we're looking for in terms of units. And here on these type of problems is also a little bit different. In basic stoichiometry problems, we typically will take the molar mass and figure out how many grams or something like that. So here we're not going to figure out how many grams or anything like that. We're interested in the volume. So when we think about the sodium hydroxide, what we have now is we just figured out the moles and we had the molarity to begin with. So molarity is moles per liter. So we have the molarity, we just figured out the moles. That will allow us to solve for liters. So the 4th step here, liters would equal moles divided by molarity. And that means that we would take our moles that we just calculated. We will use the molarity and divide by it. So we'll put the moles on the bottom here, which is 1.420 moles per liter of sodium hydroxide. Moles will cancel, and that will get us 1.42. 0.158 liters, or that is about 158 milliliters of sodium hydroxide would be needed basically to reach the equivalence point in this particular titration. So this is a typical stoichiometry problem, or typical titration problem, which hopefully you can see is really the same four basic steps for stoichiometry. The only difference is sort of at the beginning here, how we get the moles, and at the end, using molarity at the end to figure out what we're looking for. Any questions on any of those steps? All right, so why don't we try another one here? Give you a shot at it here. Let's go with, let's just make one up and hope for the best. Let's see, let's go with, what is the molarity of HCl if it required, we'll go with 75 milliliters of 0.25 molar calcium hydroxide to reach the end equivalence point of a titration. And we used, very bad wording here, but I will say we used 150 milliliters of the HCl. It's not the award-winning wording there, but we get the idea here. So basically, we took 150 milliliters of HCl, and it took 75 milliliters of 0.25 molar calcium hydroxide to reach the equivalence point. Give it a go. Take a few minutes. I'll do it as well since I made it up. Hopefully it'll work out.
Is there any Chem 200B trickery that we could use in this to make it go faster?
Not really, actually.
Oh, okay.
Actually, titration problems in 200B are actually longer than these, actually.
I didn't know if maybe there's a way to figure it out with like the pHs and logs, but that probably wouldn't work because we're dealing with volume.
Yeah, no, you kind of have to do a basic stoichiometry problem on this one. Yeah. Okay, so let's take a look and see. So really anything involving equivalence point, titrating, another common word that's sometimes used to let you know sort of a titration problem is they'll say something like neutralize. Those are all sort of the keywords to know. It's really a stoichiometry problem, titration type problem, any of those type of things. So we again want to start with an equation, and we have HCl, which is an acid. We got calcium hydroxide there, which is a base. Again, going to make salt and water. And in these strong acid, strong base reactions, again, really the water comes from the H and the OH. So that's pretty much where you get your water from. And then the salt comes from our other two guys here. So remember that when we put them together, we want to put them together correctly first. So calcium has a +2 charge, Cl has a -1 charge. So we're looking like something like calcium chloride here. At this point, once we got all the right formulas, like we've talked about before, now we want to make sure we balance it, and we want to use those coefficients. So it looks like in this case, I think we need a 2 there and a 2 there should balance it out. In terms of the information given to us for our HCl, my very badly worded problem here, we have 150 milliliters, and we're actually looking for the molarity of it. For calcium hydroxide, we have 75 milliliters, and we do have the molarity given to us. So again, in this case, we do have enough information for calcium hydroxide here to get to moles. So that's really where we want to start with. So we do want to convert our volume into liters. So you could divide it by 1,000 or move your decimal place over. So we're going to take 0.075 liters of calcium hydroxide. We're going to multiply it by the molarity of the calcium hydroxide, which is 0.25 moles per liter. That's going to cancel out the liters and leave us with moles. And it looks like we will get 0.075 times 0.25. Looks like 0.01875 moles of calcium hydroxide. Again, we're not really interested in our calcium hydroxide. We do want to get over to the HCl. If we just think about what we have in terms of the HCl so far, we have the liters basically. So we need to get to moles of HCl. So we're going to use the stoichiometry from the equation. And this is why it's important to make sure you do write the balanced equation. Not everything is a one-to-one relationship. So for every 2 moles of HCl, you get 1 mole of calcium hydroxide. So using that in our next step here, that is going to allow us to go from calcium hydroxide, which we're not interested in. So that's 1 mole of that on the bottom, to 2 moles of HCl up on top, which is what we are interested in. And if we times that by 2, gets us 0.0375 moles of HCl. By doing the stoichiometry part, we now have the moles of HCl. We don't have the liters, but we do have the milliliters. So we can get to our molarity by dividing this by the volume of HCl, which converted to liters, 0.15 liters, will give us 0.25 moles per liter of HCl would be the molarity of our HCl. Or again, you can leave it as big M HCl. Again, both are the same. Hopefully you can see again, really the same 4 steps. We have a balanced equation. We have convert to moles, mole to mole relationship. And again, here on the back end of the calculation, instead of using molar mass, we're using molarity as well. Any questions on that calculation? Our titration calculations in general, again, they're really just stoichiometry problems using molarity and volume. Although we don't necessarily have a problem like that here, it is possible to have a solution stoichiometry problem that's also a limiting reagent problem. So it is possible to do that as well. You would just be given the volume and molarity of both reactants. And again, you could basically solve it the same way as we've done before. So it is potentially possible, obviously, to have a limiting reagent problem that involves 2 solutions. You would do it the same way as a normal limiting reagent problem. Again, the difference being how you get to moles. Any questions on titration problems, stoichiometry problems involving solutions, any of those things? Okay, so molarity is pretty much the most common sort of unit of concentration for solutions, but there are different units of concentration that sometimes pops up as well. And before we move on, just sort of answer a question I was kind of asked earlier, is there sort of a shortcut? Sometimes you will see people use the dilution equation that we used earlier, that M1V1 equals M2V2. And you'll even sometimes see people call it the titration equation, that dilution equation, M1V1 equals M2V2. And will it give you the right answer? It will give you the right answer in certain cases. It will give you the right answer if the relationship in your balanced equation is a 1-to-1 relationship. If it is not a 1-to-1 relationship, like the couple examples we just did here, you will get the wrong answer. So sometimes people try to use that in titrations, and you really shouldn't use it in titrations. You really should kind of do the stoichiometry problem like we just did in these couple of examples. Will it work out in certain cases? It will, but it's really a specific case of basically a 1-to-1 relationship between the acid and the base. It will work out. Other than that, you know, I would recommend you should always do it this way. You'll definitely get the right answer. And if you try to do it the other way, a lot of times you won't. So let's then talk about some other concentration units. And these are some percent units. Kind of messed up there. That wasn't very spaced out. So this first one was referred to as percent mass to mass, and is sometimes abbreviated percent M/M. And as it sort of says there, as it kind of got all crushed together there, it is the mass of the solute divided by the mass of the solution times 100%. And the important part when you use this equation here or this formula is really the bottom part, and that's the mass of the solution. So if you remember, a solution is made up of two things. It's made up of the solute and the solvent. So you want to make sure that you get the mass of the solute here plus the mass of the solvent. And why that's important is very common in these type of problems. They will actually give you these numbers separate from each other. So they're usually separate from each other. And most of the time, people will just go with the solvent for the solution. And that's not the right answer. So you want to make sure, again, that you sort of add those guys together. There's also a couple of other sort of percent units that are very common. We could have percent volume to volume, like an alcohol here. That is the volume of solute divided by the volume of solution times 100%. And there's also percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. So these are three very common sort of percent concentrations that are used. Our mass to mass is basically grams over grams. Our volume to volume is usually milliliters over milliliters. And our mass to volume is usually grams per milliliter, very much like density in terms of the units there. So out of these three, again, really the top one here, our percent mass to mass, is really the one you usually have to worry about the bottom part. In terms of the other two, the volume of solution in problems, that's usually just straight up given to you. You don't really have to worry too much about it. We can use these percentages and you can put it into these formulas and solve for whatever you're looking for. You could also use these guys as sort of conversion factors and kind of set them up as conversion factors. So for example here, if you had a 4.5% by mass sodium chloride solution, what that would mean is you basically would have 4.5 grams of sodium chloride in 100 grams of solution. So you could kind of use it as a conversion factor. You also could flip it around if you're going to use it as a conversion factor and say in 100 grams of solution, there's 4.5 grams of sodium chloride. And you could do that for any of these sort of percent concentrations. You could say 4.5% volume to volume sodium chloride would mean that you have 4.5 milliliters of sodium chloride in 100 milliliters of solution, or in 100 milliliters of solution, you've got 4.5 milliliters of sodium chloride. And lastly, if you had something like the 4.5% mass to volume sodium chloride solution, that basically means that you have 4.5 grams of sodium chloride in 100 milliliters of solution. Or again, you can flip it around and use it the opposite way. 100 milliliters of solution is 4.5 grams of sodium chloride. So sometimes when you do these problems, it's sometimes easier to kind of take a more dimensional analysis approach and kind of use it as a conversion factor. And you can kind of see all the units and everything sort of canceling out. And, this is very much similar to what we talked about with molarity. If you have the 4.5 big M sodium chloride, you can say, as we talked about, 4.5 moles of sodium chloride in a liter, or you could flip it around and use it like that. So really all these sort of concentration units that we've seen here, you really can sort of treat the calculations like dimensional analysis, kind of use them as conversion factors. And sometimes it's a lot better to do it that way so you don't miss any of the units, especially with molarity, as we talked about. Again, people leave it as big M. They oftentimes will sort of forget all about the liters part, as we talked about earlier. So why don't you try one here and see what you come up with. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water, calculate the mass percent of calcium chloride. So we're looking for the percent mass to mass here. Okay, so when we look at this, we're taking 2.5 grams of calcium chloride with 50 grams of water. The calcium chloride here is our solute, it's the smaller part. And our water here is the larger part, which is our solvent. So again, the percent mass to mass is our mass of solute divided by the mass of the solution times 100%. So the mass of the solute would be 2.5 grams. The mass of the solution is both the solute and the solvent. So we do want to add those together on the bottom and not divide by just 50. And times it by 100. And it looks like we get something like 4.76% mass to mass calcium chloride in this particular case. Any questions on that particular one? All right, so why don't you give the next one a go? We're looking for what is the mass of HCl that's contained in 35.5 grams of a HCl solution. That is 37.2% by mass here. Okay, so let's take a look. So we have 37.2% by mass. HCl, we want to know what is the mass of HCl and 35.5 grams of the solution. So the HCl here is the solute. So remember, as we talked about when we talk about concentration and molarity, really the name of the solution is the solute. So again, if you had a sodium chloride solution, the solute is sodium chloride. So here we do have 37.2% by mass HCl, and we could really convert that into some conversion factors. So if we took more of a dimensional analysis approach, what that means is not that grams of solution. We have 37.2 grams of HCl and 100 grams of solution, or in 100 grams of solution, we have 37.2 grams of HCl. So we could really take that sort of percentage by mass and turn it into a couple of conversion factors. We have 35.5 grams of our solution. So we do want to use conversion factor on the left there. That's going to give us 37.2 grams of HCl and 100 grams of solution. And that's going to give us something like 13.2 grams of HCl in this particular case. Any questions on that? Again, you can plug and chug into the percent mass to mass equation if you want. Mass of solute, mass of solution times 100%. And basically we had this number, and obviously we had that. So when we do solve for this, it's pretty much the same math as above. You'll get the same answer. But if you're more comfortable, you could just plug it in, the numbers. You could plug your 37.2 in there, your mass of HCl up on top, your 35.5 grams times 100. And like I said, it's basically the same math as what we did above. Any questions on these percent concentrations? Percent mass, percent mass to volume, or volume to volume. Again, they all kind of work the same way. Any questions on that? Okay. So now we've talked about molarity. We've talked about percent mass, percent mass volume, percent volume to volume. There's also another sort of unit of concentration that sometimes comes up, and this is what is known as molality. So not molarity, but it's actually molality. And molality is, as it states here, it's actually abbreviated with a small m. So that's not mass in this case, that is the molality. And it's similar to molarity, except that it is technically the moles of solute divided by the kilograms of solvent, and that is the molality. And that's not to be confused with big M, which is molarity, which is moles of solute over liters of solution. So again, these two are two different things. One has to do with the liters of solution, the other one is just the kilograms of the solvent by itself. By the way, in case you ever need to go between these two, the thing that really ties these two together is actually density. So like the density of the solution is really the thing that would allow you to kind of go from one unit of concentration there to the other. And we do see molality in a number of places, and we'll see it again in a later chapter when we start talking about colligative properties of solutions. It does pop up quite a bit. So why don't we try one here? What is the molality of a solution that's made by dissolving 61.7 grams of C3H7OH in 175 milliliters of water? Carbon again is 12.01. Hydrogen is 1.008. And our good friend oxygen there is 16. All right, so see what you come up with. We're looking for the molality here. Okay, so here we are looking for molality, which again is little m. And again, that is our moles of solute divided by kilograms of solvent. So when we're looking at this here, this is what we're dissolving. So that is going to be our solute. Water oftentimes is our solvent. So we do want to figure out the moles of our solute. So we need the molar mass there of our C3H7OH. So that's going to be 3 times 12.01 plus 8 times 1.008 for all of our hydrogens. And it looks like a 16 there. And that's going to give us something like 6009 grams per mole as the molar mass. So we're going to use that to get our 61.7 grams into moles. So we'll divide by the 6009. And that will get us something. Let's see here, maybe. Calculator would turn on. There we go. All right, so that's going to get us 1.03 looks like. So that's 1.03 moles of C3H7OH. So we now have basically the top part. The bottom part we need to get to. So we have the bottom part in terms of our solvent in milliliters. So we need to get that to kilograms. So that is why the density is given to us. So the density of water there is 1 gram per milliliter. That means that we have 175 grams of water, which is our solvent. And if we convert that into kilograms, 1 kilogram is 1,000 grams. That's going to give us 0.175 kilograms of our water, which is our solvent. We now basically have both of the things that we need. So the molality here would be 1.03 moles divided by our 0.175 kilograms. And we will end up with 5.87. Now, in terms of the units, very much like molarity, you could leave it as moles per kilogram if you want, of our whatever it is there, C3H7OH. Or if you want, just like molarity, where you could put kind of the big M for molality, you could put the little m in its place. So either way is, perfectly fine, however you want to kind of do it there. And again, very similar to molarity in terms of sort of how you do the calculation and how you give the answer. Any questions on that there? Okay. So one last little, I don't know if you want to call it a concentration, but something that, again, we will see a little bit later on as well. Also later where we see molality again with colligative properties, and we'll actually see this next thing in the next chapter with gases as well. And this is what is known as the mole fraction. And the mole fraction is basically the fraction of moles of whatever you're looking at over the total moles. So it's kind of like a percentage without multiplying by 100. So all your mole fractions will be point something. And that means that if you get all the mole fractions together, they should add up to 1, which is essentially 100%. So since we're not really multiplying by 100 here, that's basically how we can figure out the mole fraction of each. So let's say we had a mixture of mole A and mole B together. So to find the total moles, we would simply add up both of those together. So moles of A plus moles of B, which means if we wanted to find the mole fraction of A, and that's what the big X stands for, mole fraction, we would take the moles of A divided by the total moles. And again, here we would not multiply by 100 as is not a percentage. And if we wanted to find the mole fraction of B, we would do the same thing. We take the moles of B and divide it by the total moles. Again here, not multiplying by 100. I'm going to try one here. Again, very similar to a percentage without that 100 multiplication. So see what you come up here. We're looking for the mole fraction of methyl alcohol here and see what you come up with. Okay, here, so we're looking for our mole fraction of methyl alcohol, and we basically have a mixture of ethanol and methanol, and we have the moles of each. So we do want to find the total moles here, and that would be simply just adding them together. So 3.328 plus our 0.929 going to give us 1.257 moles. So if we want the mole fraction of our methyl alcohol, which would be this guy, we would take the moles of our methyl alcohol, which is 0.328. We'll divide it by the total moles here. Again, we're not going to multiply by 100 or anything like that. And that would get us something like 0.261 as our mole fraction, basically 26%. We could also do the same thing for our other one. It didn't ask for it, but if we did, it would look something like this. We would take 0.929 and divide it by 1.257. And that would get us something like 0.739. Although because these were the only two parts of this, we could also got to here by taking 1 minus 0.261, and that would also get us there, as 1 would be 100% in this particular case. Question on mole fraction, stoichiometry, concentrations, all that fun stuff. Any questions on anything from this chapter? I think covers a few different chapters, I think. Okay, so then we are off to the next chapter, which I think is chapter 8, and that should be gases. And again, the notes should be up there. And obviously, in this chapter, we're going to talk about gases. We're going to learn a lot of gas laws, some of which you probably have seen before, some of which you might not have seen before as well. And we'll talk about ideal gases, we'll talk about real gases, and what happens in both of those cases. So as we go through here, there's obviously going to be some formulas that you will need to know. And those are your gas laws. And here, let's do that there. Okay, so let's talk about gases. So obviously, when we're talking about gases, we're talking about the state of matter where pretty much everybody has broken apart from one another. They're flying around. As they are flying around, there's a number of collisions that have happened between the gas molecules in the container, for example. Those collisions is what we associate with gases, which is pressure, right? So pressure is essentially what we associate with gases. As we'll talk about in this chapter, really there's kind of three variables that we come across: P, which is pressure; T, which is temperature; and V, which is volume. So a lot of gas laws really deal with those three sort of variables. In certain cases, we keep maybe one constant while vary the others. In some cases, we may keep a couple of them constant. And those are the important parts that we oftentimes will deal with gas laws. So it's good to talk about really what things, are sort of gases under normal conditions. So when we talk about kind of normal conditions, and this is different than standard temperature and pressure we'll talk about in this chapter, but under normal conditions, that's sort of everyday conditions, room temperature type conditions. That usually is basically a pressure of 1 atmosphere. That's what the ATM stands for, an atmosphere. And a temperature of 25 degrees Celsius. So 1 atmosphere and 25 degrees Celsius is what we, usually sort of refer to as sort of everyday type conditions. These are typically the conditions you find in tables when you find values in sort of tables in the back of books and stuff like that. Now, under these normal conditions, ionic compounds really do not exist as gases. And that's because ionic compounds, which are obviously made up of a cation and an anion, have a very strong attractive force to one another. And that's just basically that electrostatic force. That attractive force is what is referred to really as an intramolecular force, which means within a molecule. And that's a very, very strong attractive force. And under these sort of normal days and normal sort of conditions, we really don't find these things as gases. In order to kind of break them apart and separate them out into sort of the gas phase, it would take a lot of energy to do that. So typically what happens if you have an ionic compound and you just kind of heat the heck out of it there, it typically will start melting before it actually will go into the gas phase. And we know that, again, if you take some salt right on your fries or something like that, it's hot and all that good stuff, you don't get, sodium, metal, and chlorine gas out, which is probably a good thing. It just kind of stays there. It really doesn't break apart because of that really strong sort of attractive forces. Now, molecular compounds are a little bit different. They do, under normal conditions, sometimes come as gases. And in molecular compounds, these are guys that are sharing electrons. So these guys do come as gases, some of them, like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, methane. These are all gases under normal conditions. But a vast majority of molecular compounds are also liquids and solids at room temperature. The major difference between a molecular compound and an ionic compound is you can very easily convert a molecular compound into the gas phase a lot easier than you can, say, an ionic compound. And the very most common sort of example of that is water. So when we have water, right, if we have a couple of water molecules here, and water is polar, and the oxygen side of water is more negative, the hydrogen side of water is more positive because of that unequal sharing of those electrons. And what we get is what is known as hydrogen bonding that occurs, for example, here between two water molecules. So we get some hydrogen bonding. And it's between the hydrogen in one water and the oxygen in another. And this type of interaction is what is known as an intermolecular force. which means basically the force that holds two molecules together. And in the liquid phase, that's what you have going on. When we heat something like water in the liquid phase, because intermolecular forces are always much, much weaker than intramolecular forces, when we go to heat something like water, what ends up happening is as we heat it, we actually break the bond between two water molecules, for example. And what we're left with is one water molecule by itself and another water molecule by itself. And now they are into the gas phase as they kind of free themselves from each other. And that's what happens when we heat something like water. We end up breaking that intermolecular force because the intramolecular force is much, much stronger. In the example of water, for example, the bond between oxygen and hydrogen and this oxygen and hydrogen, these both are also what are known as intramolecular forces within the molecule, and they are much stronger. Again, that's why when we start to heat something like water, we break apart the two water molecules from each other. And if it was opposite, like the intramolecular force was weaker, when we would start to heat something like water, it would fall apart into basically hydrogen gas and oxygen gas, which clearly doesn't happen, obviously, when you heat something like water. Otherwise, you're not going to make it to the, cooking your pasta part if you're just boiling some water there for dinner. Now, when we look at substances that are gases under normal conditions, we have our normal guys that we've seen before. We have our hydrogen, or nitrogen, or oxygen, or fluorine, or chlorine. These guys are, sounds delicious. I know it does sound kind of delicious, It's dinner time. Let's go make up some of that hydrogen and oxygen pasta. I like it. Hydrogen, nitrogen, oxygen, fluorine. These are all of our diatomic molecules. And these are elements, and these are naturally how they come as gases. Ozone, which is O3, is also a gas. And then obviously our group 8 on the periodic table, they're monoatomic, which means they come basically as ones, and they are gas as well in their kind of normal sort of state. This is also a good opportunity to talk about sort of a difference between two words that is sometimes very commonly used when we talk about gases, and that is basically the difference between a gas and a vapor. So a gas is something that is normally found in the gas state. Kind of makes sense. A vapor is actually something that is not normally found in the gas state, but is something that's found, say, in the liquid state, for example, or maybe solid state, but can be converted into a gas. So the prime example of that is water that we were just talking about. When we convert water into a gas, we usually call it something like water vapor instead of water gas, because it just sounds funny when you say water gas, I suppose. But water is normally found, obviously, under normal conditions as a liquid. It can be easily converted into a gas. So we refer to water as being a vapor, while something, for example, like methane, which is normally found as a gas, is referred to basically as a gas. So there is sort of a distinction between those two words there, gas and vapor. And again, vapor is something that's normally not found as a gas, but can be converted into a gas. And in case you want to see it on the periodic table, those guys in blue are guys that are normally found as gases. Some characteristics of gases. Gases assume the volume and shape of the container in which they are in. Again, they are constantly flying around. So that means that, they pretty much fill the space uniformly as they are moving around the container. We also, as we will see sort of in this chapter as well, one of the things that makes something sort of an ideal gas is the idea that we look at the volume of the container the gas is in rather than the volume of the gas itself. And we'll talk more about that a little bit later on in this chapter. Gases are very compressible, right? You can compress a gas. As you compress a gas, right, moves everybody closer to each other, also has an effect on the pressure, usually will increase the pressure. Gases have a much lower density than liquids and solids. So usually if we calculate the density of a gas, we're usually looking at units of grams per liter. While if you calculate the density of liquids and solids, we usually think about it in terms of grams per milliliter. And here's obviously a gas. As you can see, it's filling the container pretty uniformly all the way across. So when we talk about gases, pressure is a very important sort of aspect of it. Pressure is force over area. And these are some common sort of units of pressure that we sometimes come across. We have 1 Pascal is equal to 1 Newton meter squared. 1 ATM, which is an atmosphere, is equal to 760 mmHg. mmHg is millimeters of mercury, and that equals 760 torr. And those units come from this apparatus that we see over here, which is known as a barometer, and that is what we use to measure pressure. Although in most chemistry labs and schools, they've taken these type of barometers out because pretty much it's mercury here. But basically a classic barometer had this kind of pull of mercury, also had sort of this glass tube here, and it would be kind of filled with the mercury. So as atmospheric pressure sort of exerted on this mercury, the mercury in the tube would rise or fall, if you will. And one interesting thing about mercury is the meniscus is actually reversed in a normal meniscus, actually curves upwards. And you would read from the top of the meniscus here where it curves. And we'll talk why that is in a later chapter as well. And the reason we have these sort of units is because if you look on a barometer on this little tube, there is like a ruler usually. And this ruler pretty much is either in inches of mercury, centimeters of mercury, or millimeters of mercury. So that's why it's called millimeters of mercury, because basically you take a ruler reading of how high the mercury is in the column. The torr is named after the good guy there that invented the barometer, Torricelli. So that's where we get that name there. These are good Jeopardy type questions, just in case you're watching at home. You have those answers. So 760 is also an important number because it's really a conversion factor. It is our conversion factor to go from atmospheres to millimeters of mercury or torr. So if you have atmospheres and you want either of those numbers, you're going to multiply by 760, and that would get you torr or millimeters of mercury. And that is because it is a one-to-one relationship. 1 millimeter of mercury is equal to 1 torr. So it's basically the same thing. And vice versa, if you have a torr or millimeters of mercury and you want atmospheres, you're going to divide by the 760. And that will get you your atmospheres. So these three units, atmospheres, millimeters of mercury, and torr, are very common units that we do come across a lot in chemistry. Other units are pascals. 1 atmosphere is 101,000 pascals, or 101.3 kilopascals. That's also a very common unit of pressure. Also our good PSI, right? Pounds per square inch. So 1 atmosphere is something like 14.7 PSI. Again, that's another very common conversion. And another common unit of pressure is the bar, and a bar is basically like 1.01 atmospheres. So that's also another super common unit of measurement for pressure. But I would say, like I said, these three right here are probably going to be the three that you see most of the time. And again, that means that 760 is a really important sort of measurement or number to remember to allow you to convert between one or the other. Any questions on that there? All right, we will lay it up there for lecture here today. We'll do lab at 7:15. I'm going to go look at the schedule and see what we got coming up. I